Hello everyone. Today is the 59th day of Leetcode 75 challenge. Let's begin with the 59th question. Question 1137, nth Tribonacci number. The level of the problem is easy. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given an integer n and you need to compute the nth Tribonacci number. If you can relate this with Fibonacci, Fibonacci series, right? It is the same one as the Fibonacci series, the Tribonacci series. In Fibonacci, we used to have T0 plus T1, right? But here there will be another number T2, right? If you can see here, but instead of starting with two predetermined terms, it starts with three, with T0, T1, and T2, right? And each term thereafter is the sum of the previous three terms. Basically, Tn will be equal to Tn minus 1 and minus 2 and minus 3. And in Fibonacci, if you remember, we just had only two terms, right? It's the extended version of the Fibonacci series. And at least n has to be 3, right? Because we required three numbers for our T of nth number, okay? Your goal is to return the Tnth value, and you can assume that input value for n is a non-negative integer and within a reasonable bounds. The result should be the result should be returned as an integer. Okay, so this is a simple question. As we know about Fibonacci, we can jump down into a Tribonacci one. The constraint of the problems are n value is from 0 to 37, and the answer is guaranteed to fit within 32-bit integer, that is answer to 2 to the power 31 minus 1. Okay. So I hope you understood the problem explanation. Let's move to the next slide. Now let's understand the input output explanation. So if n is equals to 4, our output is 4. How? Let's see. Here n equals to 4, right? We have to find the Tribonacci fourth number. Okay. So T0 will be what? 0. T1 will be 1. T2 will be 1. Okay. T3 will be 2. How to? T0 plus T1 plus T2, right? And T4 will be what? 4. How? T3 plus T2 plus T1. Okay. If you add this, what you get? You get 4, right? This is what our output is here. It is 4. Okay. So I hope you understood the input output explanation. It was pretty straightforward. So let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's do it by understanding the goal first. We are given an integer n. We understood that, okay? And our task is to compute the nth Tribonacci number denoted as T of n or Tnth, okay? Which basically means that T0 equals to 0, T1 equals to 1, T2 equals to 1. This is the first three digits of the Tribonacci series. This is a rule, you could say that, okay? And n has to be greater than 3 or equals to 3. Therefore, then and only we could calculate the nth number Tribonacci series. For example, if n equals to 4, as we see the previous example, it has to be this way: 2 plus 1 plus 1 equals to 4. Okay. So our goal is to return the value of the Tnth as an integer. Now, the brute force approach would be compute values multiple times and be highly inefficient due to the repeated subproblems. If you remember the Fibonacci series, which we used to solve mostly by using a recursion solution, right? And the time complexity for the Fibonacci used to be 2 to the power n, right? But here the time complexity will be 3 to the power n, which will be highly inefficient, and because of that it will fail our test cases. So to avoid that, what we could do, if you remember, if recursion is a solution but it does not solve anything, or there is out of bound or time complexity issue, the thing which comes to our mind is DP, which is dynamic programming, right? And here you could see we have repeated sub problems, so definitely dynamic programming will help us in that particular situation. Okay, so let's visualize this process now. Okay, we all know that for this particular scenario, what will be our base cases? Base cases will be if n equals to 0, we have to return n, okay, because 0 output will be 0. If n equals to 1, we have to return 1, or you could write here 0, okay, because 1 will give you definitely a 1 only. If n is equals to 2, then also we have to return 1, because there have to be at least 3 numbers with us. Okay, we know we have this clarity with our situation. In Fibonacci we used to take only these 2, but in Tribonacci we need these 3 values. Okay, pretty simple. Okay, so the second thing which comes to our mind is the recursive code. Usually in Fibonacci, what happens is that suppose if we have a variable fun here, it will be suppose function name s n minus 1 plus s of n minus 2, right? What will happen in Tribonacci? We will add another which is s of n minus 3. Now this will be our function call. Pretty simple. Now how this will work? Okay, let's check that one. If I draw a recursion tree, it will be like this: t of n. Okay, for to calculate this t of n, we will be required t of n minus 3, t of n minus 2, and t of n minus 1, right? And then to calculate this t of n minus 1, we will be required t of n minus 4, t of n minus 3, and t of n minus 2. Definitely, to calculate this t of n minus 3, we will be required t of n minus 4, n minus 5, and n minus 2. Correct? Similarly, t of n minus 2 will be t of n minus 1, then n minus 3. So similarly, to calculate t of n minus 2, we will do the same scenario. Correct? So if you could see here, this was n minus 4, this is n minus 3, this is n minus 2, right? So if you could see, this n minus 3, this is 3, right? T of n minus 3 and t of n minus 3 are repeating, correct? T of n minus 4 and t of n minus 4 is also repeating, right? And here t of n minus 2 and t of n minus 2 is repeating. So we have repeating sub problems. So to avoid that, what we will be doing, we will be using dynamic programming, as I explained earlier. And by storing already computed value, which is memoization, we avoid recalculating them, significantly improving the performance. This way we reduce the time complexity from exponential to a linear, making it scalable for larger inputs. Okay, so I hope you understood this visualization process. Let's move to the next slide. Now, how we can simulate this? Simple as that, we will require a function which will be having n value which is given to us and the dp, right? And we will just initialize the dp as dp with minus 1 with n plus 1, right? And we will have at each call we will check if n is 0 or 1. Base cases, if n is 2, we return 1. These are the base case, as I explained earlier. Otherwise, what we will do, we will try to compute, this way: dp of n equals to suppose the function name is rec, right? Rec of n minus 1 plus rec of n minus 2 plus rec of n minus 3, correct? And at the end, after completing or writing all this, after the recursion is done, we will return dp of n. Okay, as you could see, I have written it here already. So this is the simple simulation process. I hope you understood this. Let's move to the next slide. Now what we figured out? We figured out that the recursive approach without memoization leads to an exponential time complexity which is 3 to the power n, and memoization optimizes it to a linear time complexity, which I will discuss earlier, which I will discuss further. And this dynamic programming approach ensures that we compute each Fibonacci number from 0 to n only once. Okay, basically reducing by not calculating the sub problems again and again. Okay, so I hope you understood the complete intuition. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach, how we're gonna solve it. This is the edge case or the base case which we will be writing inside the fun function or recursive function which we will write. Okay, so within that fun function, what we will have? We will have n and dp, right? And within that, we will write if n is less than or equals to 1, we will return 1. If n is equals to 2, we will not return 1, we will return n, because it could be 0 or 1, right? And when n equals to 2, we have to return 1 only. Okay, and at step 2, we will prepare for memoization. This memoization preparation is basically done within the base function which is given to us, and that means that we will create a dp array having all minus 1 with n plus 1 as the size. Okay, this sets the foundation for building up the solution using recursion and memoization. Okay, now at step 3 we start the backtracking process or the DP or the recursion. Okay, the helper function which we will define rec or fun, whatever you could name them, no issue. We will pass n and DP in it. Okay, and we will just write the base cases this way. I will write it again. Return n if n is equals to 2, return 1. Then if DP of n, if it is not equals to -1, just return DP of n, because we have already calculated this. Suppose if it is 3, DP of 3, and since we have already calculated DP of 3, why we will calculate again, right? This is the common template of a DP solution. So we will return DP of n directly from there. Otherwise, we will write DP of n and just we will call the function here rec or fun, whatever, n minus 1 DP plus rec of n minus 2 DP plus rec of n minus 3 DP. Okay, so this way we will calculate the function, and this allows us to break the problem into smaller and overlapping subproblems and reuse previously solved result. Okay, this is the complete backtracking code which we will be writing. So I hope you understood this. So since I already talked about at step 4 what will happen, since I already talked about this DP when not equals to -1, because it is already computed, and what will happen after this complete solution within the fun function or the recursive function, after completing this at step 5 we will return the final output. That will be, if you remember, return of DP of n. Okay, and at the main function which will be given to us, there we will just write return rec of, we will pass n and DP there. Correct? So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So this is the code exactly which I wrote. Okay, this is the declaration of DP, initialization of DP array. This is the function which we will define, fun. We will call it here. This is the base cases, and this is the already computed value, and this is the main recursive or DP solution. Okay, and after this complete solution is done, we just return the DP of n. Now for this, the time complexity is O of n, because first of all we are using a top-down approach. Okay, which is memoization, and each state n is computed only once. Okay, and stored in DP of n. For every n, the function make at most 3 calls or recursive calls. Okay, which is basically n minus 1, n minus 2, n minus 3. But due to memoization, already computed states are not recomputed. That is why the time complexity reduces to O of n, since there are n state and each state takes O of one time after memoization. Because suppose if you calculated DP of 3, okay, it takes time complexity of O of 1. Okay, and since there are, suppose we have to calculate Tribonacci series for n, which is 6, right? So it will be calculated only one time, 2 times, 3 times, 4 times, 5 times, and 6 times. So this becomes only O of n. Okay, if I had to calculate for 6 multiple times like we were doing in recursion, then the time complexity would have reached to 3 to the power n. Okay, and simply space complexity is O of n because the maximum space taken by a DP is of n plus 1 space. That's all. So I hope you understood the code and time space complexity. Let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. So here we have n equals to 4, right? N equals to 4. Let's try to do the dry run. I have brought down the code here for our understanding. So we have the DP. N is 4, right? So 0, 1, 2, 3, 4, 5. Okay, and everything is initialized with -1. Great. So let's call the function. We're standing at here. Now, right now, n value is 4, correct? Is it less than equals to 1? No. 2? No. Is DP of n is not equals to -1? No. So what will happen? Let me draw the recursion tree. That will be much more easier, I guess. So n is equals to 4 right now. Okay, so for 4 what will happen, we will calculate n minus 1, so it will become 3. N minus 2 will become 2, I guess, and n minus 1 will become n minus 3. N minus 3 will become this one. Okay, n minus 3. Great. Now what will happen, now this function will be called first, right? So for this, again we will come here, these conditions are false, so n minus 1 will become 2, n minus 2 will become 1, right? And n minus 3 will become 0. Okay, great. Again for this, breakdown will happen. Now is n is equals to 2, yeah, so what will happen, it will return 1. Okay, great. Now this will be called n minus 2, which is this one. If n is less than or equals to 1, it will return n. What is n right now, it is 1, right? First this will be called, now this will be called, right? So n equals to 0, so what will happen for n equals to 0, it will return 0 itself. Okay, so 4, so this is done, so we will add this. Now 1 plus 1 plus 0 gives me 2, so this complete part will return 2. Okay, so we already know for n, for t of 3, output is always 2. Okay, now this is done, then we will come to n equals to 2. Okay, I will clear this up. Now n minus 1 will happen, will be 1, n minus 2 will be 0, and this will be basically um, minus 1. Okay, so for 1, 1 will be returned, right? Because we will come back here. For 0, 0 will be returned. For minus 1, 0 will be returned. Okay, so addition of this will return 1, right? So this will be 2, this will be 1. Okay, now for n equals to 1, n minus 1 will give 0, this will give minus 1, this will give minus 2, right? So when n is less than equals to 1, it returns 0, and this 3 will return as 0 itself. Okay, because n is 0 here, so this will be 0. Okay, now for n equals to 4, so recursion will go back, right? It will return 0. Okay, but if you can see here, if you remember, if t is 0, it returns 0 definitely. If t is 1, it returns 1. If t is 2, it returns 1, right? So here we got 1, here we got 2, which is correct. If you remember, t3 is equals to 2, right? And here if you can see, n is 1, correct? So if it is 0, it will return 0. If it is any negative number, it will be ignored definitely. Okay, so when we are here, and when this function is called for t of 4, t of 3 will return 2, will be at 2. T of 2 is 1, right? T of 3 we got 2, and t of 1 is 1, right? So this will return 1. Okay, so when we add all of this for this t of n of 4 in this scenario, we get 4. Okay, so when this particular call is done, what will happen, d of n, which I forgot to update here, but I hope you understood the recursion, right? So this is the same thing, the t of 4 will be having the value 4 with it, and this value t of 0 will be having a 0, this would have been 1, 1, and this would have been 2. I forgot to update this, by bad, but I hope you understood the recursion. So this is the same thing which we have to update in the DP solution, which I just forgot to do. Okay, so what happens when DP of n is returned, which is 4, so we get the 4 as the output. Okay, so if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the code. After that, do a dry run by yourself on 2-3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. So let's move to the next slide now. Now, since you're familiar with the problem and the solution, let's move to the Leetcode and code the solution. So we will start by initializing the DP array of size n plus 1. Why we initialize with n plus 1? Because we are taking here as one base indexing, right? Because you have to return one based value, and so we don't have so we don't have the runtime error or overflow or garbage value returned as a DP array. That is why we have to take n plus 1 as our secured size. So we return the self dot function n comma dp. Okay. So, okay. Definition or define fun self n and dp. Okay, great. If n is less than or equals to 1, return n, right? If n is equals to 2, we return 1. If dp of n, if it is not equals to -1, which means it has already been calculated, so return the value of dp of n. Otherwise, dp of n equals to self dot fun of n minus 1 comma dp. Let me copy this. Paste, paste, and this will be 3. This will be 2, right? And then we will just return dp of n. Okay. Let's try submitting for the sample base cases or test cases. Okay, there is a runtime error. Self is not defined. Okay, it is a spelling mistake. Let's try again. Now let's submit all the final test cases. So we have successfully submitted our solution. Now code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.